So, hi everybody, my name is Steffen Christgau, and together with Marius Knaust, I'm a research associate here at the supercomputing department at Zuse Institute in Berlin. And we want to share our experiences with getting from CUDA to data parallel C++, and then back again to Nvidia GPUs and also to FPGAs. And if you attended the keynote today, we heard Michael Wong talking about his dream of having a programming model or programming language that can address different architectures, and having one language to address multiple of them would be fine for him. It was his dream for a long time, as I heard. And we also have this expectation from oneAPI to have this a single source code and run it on different hardware platforms. And we wanted to know how this actually fulfills, or if it fulfills. The question now is, how can you answer this question? Do you start writing an application from scratch, or do you have any other opportunity? And one other opportunity is to use a compatibility tool that is coming with the oneAPI packages, which helps you to migrate an existing code base, like a code base that is written in CUDA or for CUDA architecture, and migrate it to data parallel C++. And we wanted to look at how this actually works out with a real application, not only a toy example. And in this talk, we want to share our experiences with the application named EasyWave. EasyWave is an application that was originally written at the German Research Center for Geosciences. And it's an open source tsunami simulation, which in case of a seismic event, so an earthquake or so, collects or gets input from sensors, for example, and starts to compute the propagation of not a seismic wave, but a tsunami wave. And it computes the arrival times and wave heights in a region of interest, like in the Pacific Ocean shown in this graphics here. And it is used in early warning centers to get an evaluation and an assessment of the risk in a particular region at the ocean border, at the ocean coasts. And it's originally written in C++, and it has support for oneMP and CUDA by having different classes for each architecture, so to say. And at its very computational level, it's a memory-bound stencil application that computes the propagation of the wave based on a growing compute domain. So it restricts the computation first to a very small region where the earthquake happens, and then it starts expanding the compute domain as the wave propagates. And so we had this code base which addresses CUDA among oneMP and also oneMP. And then we started heading towards oneAPI using the compatibility tool. And this is really a straightforward migration process, because you can put your existing code, even you can also select the whole project or choose single source files and put it into the compatibility tool, which assists you in migrating the code into data parallel C++ code. And it's actually the case that you get code out of it that is still readable, and you can still maintain it to adjust it for further optimizations and so on. And another nice thing is that it only touches the CUDA related parts. So everything else is basically unmodified. And places where you where the compatibility tool gets into regions where it can't do anything or there's problems, it annotates your code with comments, and you can fix those issues manually if there are any. However, this is really a convenient process, as I said, and it's a good starting point for further development and further optimization, because it relieves you from the tedious task to rewrite all the code and doing the syntactical changes that are required to get the CUDA code into data parallel C++ code. And in the outcome, in our case, we had only a very minor increase in lines of code. So the code amount just increased by 5%, which was mainly due to the fact that launching a kernel in Sickle takes much more lines than in CUDA. In CUDA, it's only a single line, where in Sickle you have, let's say, 10 to 15 lines or so, depending on what you're doing, to actually launch a kernel. And everything else is almost unmodified, as I said. Even the kernels are only modified in very minor aspects, basically getting the IDs of the elements in your buffer or array you have to compute, and everything else is untouched. So you still have full control over your actual computation that is going on. It's not scrambled or cryptographically, let's say, modified by the compatibility tool. And one important thing that comes out of this process is a source code that actually runs on different architectures. To spoil a little bit of this talk is that the code runs not only on CPUs, but also on GPUs, also made by Intel, and also on FPGAs. And even more important for every application, I think, but for EasyWave it is very important because of its use case, is that the data that is computed by the application on all of these platforms is valid, which means that the numerical output is basically the same. There are some minor deviations which we attribute to the differences in the architectures and maybe different optimization processes done by the compilers, but in principle, all the data is valid. So, and having a look at the performance of the application, we have a small snapshot here from our experiences on the Dev Cloud, which is provided by Intel, and where you can run your oneAPI workloads on different architectures. And here you can see a performance evolution and performance improvement, so to say, on coffee-like Xeon CPUs, which have integrated graphics. I think, as we heard before in the talk before mine. And here you can see that performance gradually improved with versions released in the time in the beta phase of oneAPI. And if you modify your code based on this migration process, again, you can remove performance issues that you introduced yourself into the code, and you get a more speed up just because of code restructuring, so to say. However, if you remember, the code is originally written also for CUDA GPUs. Now you may have the problem, so to say, that you have Nvidia hardware, but you have now code that is running, or that is not CUDA code, so to say. But luckily, you can just grab your data power C++ code now and compile it with a compiler that supports CUDA. And this is actually a contribution by Codeplay to the Intel open source LLVM compiler. And now you can just compile this data power C++ code without any adjustments except for the workgroup size, which you may tune for performance reasons. And you can actually run it on an Nvidia GPU. And when it comes to performance, actually there's only a very minor performance penalty when you switch from CUDA code to this migrated data power C++ code. In case of EasyWave, we have only a penalty of 4%, which is very acceptable, as we think. And if we go further, then we can not only use our code to run on a GPU like Intel GPUs or Nvidia GPUs, but we can also run the workload on FPGAs. And you may ask yourself, what should I do to run it on an FPGA? Well, the only thing you have to do, as in our case with EasyWave, you can grab the migrated code and build it with the data power C++ compiler. And we were able to actually build different versions based on modifications we thought were valuable for the FPGA, using the data power C++ compiler and target the Intel Stratix card here. And again, this code version produced correct values, so the outcomes are still within minor deviations acceptable. However, in our first attempts, we noticed that the computed domain was not exactly the same as in the reference code. So actually, the FPGA version first computed the whole ocean or the whole compute domain that was provided in the problems that we put in as input. but it was too large. As I said in the introduction, the compute domain expands over time, but it was not the case in the FPGA case, in our FPGA compilation or in the FPGA runs. And it turns out that the atomic operations did not work as expected. However, we were able to rewrite the code such that it didn't use the atomics, but used a loop to detect where it is required to expand the computational domain. And by doing so, we were actually able to increase the computational performance of the EasyWave code on an FPGA by a factor of 2.6 compared to this initially migrated source code. And it shows again that based on this migrated code, you are still able to modify your code with only, in our case, very few fixes to get it actually compute the exact results. And we are still working on it to get further optimizations into the FPGA version and optimize the code for FPGAs. And we are keen or interested in how far we can get for this, let's say, exotic platform here. And to sum up this talk, this lightning talk, I want to say that the migration to data parallel C++ is actually feasible, and it's not complicated if you use a migration tool. And that Michael Wong's dream of having a single code base that runs on different platforms actually became true now. Just as we can say from our point of view with the EasyWave code, it is now able to run on hardware like CPUs, GPUs, and FPGAs. And concerning performance, it is on par with the reference CUDA code, which is, I think, a very interesting result for this project and the oneAPI initiative overall. So with this, I'm coming to an end, and thanks for your time. And if you have questions, feel free to ask them in the Slack channel.